So after you finish this lecture series, you're going to be able to explain the relationship between energy and phase changes, identify phase changes relative to a heating and cooling curve. You're going to be able to relate melting point, boiling point, vapor pressure, and volatility to intermolecular forces, as well as relate these features and phase changes to pressure and temperature changes within systems. So the phase that a specific substance is in is going to be determined by three main things: the temperature and energy that is put into the system or removed from the system, the pressure that's being exerted onto the system, as well as the strength of the intermolecular forces. So as we know, solids, liquids, and gases, as we see in the diagram here below, all have unique spacing features as well as relative energetics associated with each. So any substance that's in the solid phase is going to have lower energy and closer particle spacing than that same substance in the liquid phase and that same substance in the gaseous phase. Now, we know that as we add energy, we're going to change from solid to liquid to gas. Now, the energetics of this are nicely diagrammed here. If we look at this diagram here, we have energy of the system. And basically we have the various phases of matter. The solid starts down here. If we add energy in, which is indicated by a red arrow indicating an endothermic process, if we add energy in, we can go from the solid to the liquid and basically melt that liquid. Vaporization is going to be represented when we go from a liquid to a gas. And these processes require us to add energy into the system. Now, removal of energy is represented by blue lines, and you see condensation, freezing. And of course, these processes are exothermic because the system is losing heat. So these transitions or these changes are going to be represented with specific enthalpy values. So delta H of fusion, delta H of vaporization, delta H of freezing, delta H of condensation. And these all represent phase changes, or the energy associated with phase changes when going from solid to liquid or liquid to gas, or what have you. So we're going to go ahead and look at heating curves. Heating curves are going to have several main components. You're going to have your temperature along your y-axis and your heat energy added along your x. You're also going to have a line. There are sloped components. Those sloped components are always going to be your phases of matter, such as solid, liquid, or gas. And you're going to have these plateaus, and along the plateaus are your phase changes. Okay, and we're going to talk about why there are different slopes associated with the states of matter versus the actual phase changes themselves. Okay, so remember guys, temperature is not the same as heat. Okay, and so if we keep those two separate in our head, we can go ahead and look at the explanations of what's happening along this curve. Okay, so as you're adding heat to a solid, what ends up happening is the particles inside that solid start to vibrate faster and faster and faster. And as they start to vibrate faster, their kinetic energy is increasing, and subsequently that means their temperature is also increasing. And that's why we have a sloped line. Now, eventually we're going to get to a point where the heat that we have added is no longer going to be going into increasing that kinetic energy, but instead is going to be used to separate out the molecules within that solid. Okay, and so what happens is that we're still adding energy into this system for the substance. However, that energy is no longer going into making the particles move faster. What's happening is that those particles are now being separated from one another. So in that case, the heat that's being added along a phase change is actually going into separating out those particles and subsequently increasing their potential energy. This process of increasing of potential or kinetic energy and then an increase in potential energy over the phase change is going to continue to occur along this heating curve. Now, if we were to go ahead and look at a cooling curve, we would expect the same process, except that instead of an increase in kinetic energy or an increase in potential energy, we would see decreases in all of those. Okay, so let's go ahead and clearly define melting point. Okay, so your melting point, guys, is the temperature at which the solid changes into a liquid. Okay, so that temperature is the measure of the melting point. The delta H of fusion, okay, that is the energy that's being added during that phase change in order for this melting to occur. Okay, so please make sure, guys, that you're differentiating between melting point and its relationship to temperature, as well as how fusion, or the enthalpy of fusion, is related to the melting process. Okay, now another thing I want to point out, guys, is that freezing point is just going to be the reverse process seen on the heating curve in the previous slide. Okay, so we know that as we go from a liquid to a solid, we are freezing the substance. Okay, so what's going to happen there is that the temperature change at which that occurs, that's going to be your freezing point, right? And of course, the energy being lost during that process is going to be known as enthalpy of freezing. Now, because these processes are directly connected to each other, they're just the reverse of one another, they're going to be equal in magnitude with respect to their enthalpies, but opposite in sign. Okay, so obviously the system during the freezing process is going to be releasing that heat energy. So we have a negative sign here on our enthalpy of freezing to show its relationship to enthalpy of fusion. Understanding what vapor pressure is going to be very important for some of the future slides we're going to look at. So let's go ahead and define it. So vapor pressure is the pressure exerted by a vapor in equilibrium with a condensed phase, so something in the solid or liquid phase, at a specific temperature or given temperature in a closed system. Okay, so what happens, guys, is when we have a liquid or something in a closed system, it is possible for it to go into the vapor form or the gaseous form. And what ends up happening is that eventually a specific number of particles, okay, or a number of particles are going to enter into the upper area of the container above the liquid phase. Okay, so we have our liquid down here, and these little circles are representing our vapor. Okay, and so what ends up happening is as this production of the vapor reaches a certain point, what's going to happen is we're going to create something called a dynamic equilibrium. And basically a dynamic equilibrium is achieved when the rate of vaporization, okay, so the production of these gaseous particles, okay, seen above, is equal to the rate of condensation. Okay, so what ends up happening is, okay, this process is ongoing, back and forth, liquid to gas, gas to liquid, back and forth, back and forth. Okay, and so this dynamic equilibrium is called such because it's dynamic in the sense that we're going back and forth, and it's at equilibrium in the sense that the number of particles of the vapor that are produced versus the number of particles in the liquid phase, those are going to overall remain constant with respect to themselves. So I'm not saying they're the same. I'm saying that however many vapor particles we have above the liquid, that's going to remain constant, and the quantity of liquid that we have below at equilibrium will remain constant. So things such as temperature, things such as pressure, and of course intermolecular forces can all affect the relative vapor pressure of a specific substance. So the consideration of vapor pressure, of course, is going to be important for certain phases of matter. So boiling point is the temperature at which vaporization is going to occur when you are heating a substance. Okay, and this will occur, or boiling will occur, when vapor pressure is equal to the external atmospheric pressure. So what happens is that as you increase the temperature, the number of particles that are being released above the liquid is going to increase. As that increases, the vapor pressure increases, and once the vapor pressure, again, is equal to the external pressure, that's when boiling happens. Now, 1 atm or 1 atmosphere is basically the standard for what normal boiling point is going to be based off of. However, you need to understand that if you change the atmospheric pressure, you're going to also change your boiling point. Okay, so if you decide to go and stand on Mount Everest and try to boil some water, that decrease in atmospheric pressure is going to also decrease your boiling point. So what ends up happening is that your water will start to boil at a temperature lower than it would at, say, sea level. So in that context, obviously, say you're cooking something and you're in higher altitude, the reality of it is that the temperature of the water is going to be lower than anticipated when that boiling starts to occur, so that affects cook times and things of that sort. So you want to make sure that you understand this relationship between atmospheric pressure and your boiling point, as well as vapor pressure and your atmospheric pressure. Now, the process, or the temperature at which this process occurs, is known as the boiling point. and your energy added during this process is going to be known as your enthalpy of vaporization. So the energy that you have to put into the system in order to get it to vaporize is known as your delta H of vaporization. Okay, another thing I want to point out is obviously the reverse process, otherwise known as condensation. So going from a gas to a liquid. Condensation, again, is going to be the reverse of our vaporization process. Now, because they're just the reverse of each other, the energetic value should just be equal but opposite in sign. And since condensation is an exothermic process with respect to the system, and that gas is giving off its energy in the form of heat, you're going to have a negative sign in this equality for the condensation component. Okay, so the last thing I want to talk about here is volatility. Before we do that, we need to talk about evaporation. So evaporation, guys, is the change of a liquid to a gas at temperatures that are below the boiling point of that substance. Okay, so maybe you're adding some heat in some way, but you're not adding so much that you're increasing it to the temperature in which boiling is going to occur. Now, volatile liquids are liquids that are going to evaporate more readily than others. So like perfumes or gasoline or organic solvents, what have you. But basically what's going to be a common feature amongst really volatile liquids is going to be the fact that they have low intermolecular forces. Okay, now low intermolecular forces mean that they require very little energy in order to separate out the molecules. And basically that's why high volatility substances usually have very low molecular forces. Now, if they're able to go from liquid to gas phase very easily, that leads to obviously higher vapor pressure. Now, if you increase the temperature, like take a little bit of your perfume and put it on your neck, the temperature or the energy from your body heat will increase the temperature in the liquid, and that will basically help overcome the intermolecular forces and make it easier for the liquid to enter the gaseous state. So now that we've covered volatility, we're going to go ahead and move on to other topics.